So in last lecture, we designed DFA for W starts with A or AB. Now this is another standard problem statement. W contains substring. Now in this lecture, we are going to design DFAs for W contains substring A, W contains substring AB, and then ABAA. Now this part is relatively easy and straightforward. For AB, it is also doable. But when it comes to designing DFA for W contains ABAA, we have to understand logic and develop the procedure. That is also easy, but we have to understand logic and develop the procedure. So let's start with the most easy part. Alphabet contains A and B, and language L1 is W such that W contains substring A. Now if we consider simply string A, it contains substring A, it is part of the language. Here also we have substring A, here we have substring A, here also we have substring A. But if you consider string epsilon, it does not have substring A, it is not part of the language. For B, B power 2, B power 3, they do not have substring A and they are not part of the language. So let's design the DFA. We take initial state P. Now here we have seen that as long as only B's are coming, we are not going to have substring A. So here at initial state, we draw this loop. So in this loop, we are handling only B. Now if A comes, we go to state Q and mark it as a final state. Some B's are coming. Now we find A. So we have processed only this much part of the string, but here we find A and we go to state Q, but now we are sure that we found the substring A. So whatever comes next, we have to handle that part and accept the string. Here we reach to final state Q. Whatever comes next in the string, we process it and accept the string. So for W contains substring, for this type of problem statement, final state will have this loop which processes all the symbols. The reason is, once you find substring, you do not need to worry about what comes next. Once you find the substring, you accept the string. So once you find the substring, you process rest of the string in this loop and accept the string. So this is the required DFA. Now let's design DFA for W contains substring A. So first we will draw the basic part of the DFA. Initial state is P, and then we require substring AB. So this is not complete DFA. This does not mean that first symbol should be A, second symbol should be B. This is not the meaning of this DFA. This DFA is not complete. Now again, as long as only B's are coming, while processing the string from left to right, as long as only B's are coming, we are not going to have substring AB. So here we draw this loop. This loop handles B. Now if A comes, we go to state Q. So here we are in state P, here we are in state P, here we are in state P. Now we found A, we go to state Q. The string processing is not complete, only this much part is complete. Now after this, if we find B, we go to state R. But what if A comes? Now once you reach to state Q, as long as A's are coming, you remain in the same state. Because using this A, whichever is the last A, you can use that A, then get some B and reach to final state. So as long as A's are coming, you remain in state Q, and once you find B, we go to state R, because here we find substring AB. Once you find substring AB, it does not matter what comes next. Once you find substring AB, you simply process next remaining part of the string and accept the string. So here in final state, we process all the symbols in the loop. Here also in the final state, we process all the symbols in the loop. The reason is, once you find substring, whatever comes next, you accept the string. Whatever comes next, you process that part in the final state using this loop and you accept the string. Now regarding number of states, here the condition is substring A, length of A is 1. So if you consider n equal to 1, we require n plus 1 equal to 2 states. This is n plus 1. Here the condition is AB. So length of AB is equal to 2. So if we consider n equal to 2, we require n plus 1, 3 states. So this is easy part because this length is small. If we go for substring ABAA, then in that case we have to understand some logic and develop the procedure. So let's handle condition W contains substring ABAA. Now let's understand the logic first. Let's say some string is being processed by the DFA. It started here. We started processing the string from left to right and we reach here. Now when we are here, these are some of the last seen symbols. Now in this case, can we use any suffix of the last seen symbols and get substring ABAA? Can we use any suffix of this part and come up with substring ABAA? So in this case it is possible. We can use AB. After this, if AA comes, then we get substring ABAA. So in this case we are able to use some suffix of the string processed so far. In this case we are able to use suffix of string processed so far and then get the required substring. Now consider this part or this case. This is where string started. We started processing the string from left to right and now we reach here. Now this is the last part of the string processed. So we reach here. This is remaining part of the string and this is the last seen symbols. These are last seen symbols. Now in this case, can we use any suffix? Can we use any suffix of last seen symbols and get substring ABAA? In this case, it is not possible. In this case, we cannot use any suffix of last seen symbols to get the required substring ABAA. In this case, if we want ABAA, we need to have complete substring ABAA. In this case, we were able to use this much part of the suffix, this much part as suffix. So AB is the suffix of last seen symbols. If we get AA, we get required substring ABAA. Here we do not have any such suffix. We require complete ABAA. So we are going to use this logic and construct the DFA. Now this is the basic structure. As long as B's are coming, we cannot have substring ABAA. So here we draw loop for B. Now if we find ABAA, we go to final state and we find substring ABAA. So at final state we have loop for all the symbols. Now here we have to calculate transitions. Now we are going to calculate transitions such that state Q remembers last one symbol seen is A. We are going to calculate transitions such that significance of state R is last two symbols are AB. For S, last three scene symbols are ABA, and for T it is ABAA. So if last two symbols seen are AB, so if we get AA, we go to final state. If last three symbol scenes are ABA, now if next symbol is A, we get substring ABAA and we go to final state. What about initial state? Significance of state P is last scene symbol is B or BB or B power 3 or B power 4. Here substring length is 4, so we stop at B power 4. You will understand this part when we complete the DFA. Now let's complete all the transitions. We have to calculate all the transitions. At state Q, if B comes, we go to state R. But what if A comes? So here, when we are in state Q, last scene symbol is A. And we are checking what if another A comes. So we have to check whether there is any state where last two symbols are AA. So in this case, there is no such state. So what we do? We ignore the leftmost symbol and we check if is there any state where last scene symbol is A. So it is state Q itself. So we add this loop. So what does this mean? So significance of state Q is last scene symbol is A, another A came. After this A, if BAA comes, after this A which is processed in this loop, this A is processed in this transition, this A is processed in this loop. After this, if BAA comes, we process BAA and we get substring ABAA. So we use this suffix of last scene symbols. Now let's come to state R. Now significance of state R is last two symbols are AB. Now if A comes, we go to state S. But if B comes, what to do? We use the same logic. First check, is there any state which remembers ABB? There is no such state. So we remove the leftmost symbol. So check if there is any state which remembers BB. So it is this state. So from R, if we see B, while in R, if we process symbol B, we come back to state P. The reason is, after processing ABB in the string, we are processing the string and here the last three symbols are ABB. We are in state R, which remembers last two symbols are AB and another B comes. If this happens, we cannot use any suffix of this part. We cannot use any suffix of this part and get substring ABAA. Now we require all four symbols ABAA to get the substring ABAA. So that's why this transition is added. Now coming to state S. State S, last three symbols are ABA. If A comes, we go to state T. But what to do if B comes? So let's check, is there any state which remembers ABAB? There is no such state. From left we remove one symbol. Now check if is there any state which remembers BAB. There is no such state. Again, remove leftmost symbol. Is there any state that remembers AB? So it is state R. Right now we are calculating transition of state S. If B comes, we come to state R. Now what does this mean? Significance of state S is last three symbols are ABA. We have calculated transitions such that if last three symbols are ABA, the DFA will surely come to state S. That is how we have calculated the transitions. So DFA is in state S. Now B comes. So some string is processed. Some string is processed. After that AB is processed. While in A we are in state S. If B comes, we come back to state R. If B comes, we come back to state R. And now we can use this suffix AB, which is significance of state R. State R remembers last two symbols are AB. Now we can use AB if AA comes. If AA comes, we get substring ABAA. So A, B, A, we find our substring and we can go to final state. Here in state Q, A, B, A, we find substring ABAA. But for state R, if B comes, we cannot use any suffix. So we have to come back to state P and then get all the four symbols ABAA. So this is how we have calculated all the transitions. B, A, B, A, B, A, B. In case of substring, we do not have to calculate transitions at final state, because significance of state T is that if the DFA processing is in state T, it means last four symbols are ABAA. That means we have found substring ABAA. So whatever comes next, we should process using this loop and accept the string. Now regarding number of states, length of ABAA is equal to 4. So n equal to 4 and number of states is n plus 1, which is 5. Now you may find that these calculations are time taking, but it is not the case. If you practice enough, then this is a very fast process. And in GATE exam, usually this length is up to 3 or 4. It will not exceed more than 3 or 4, the length of the substring. So you have to practice. So in the link given in the description, you can download the document and there are some more practice problems. For example, substring AABB, substring BABA, substring BBBB. So these are some more practice problems which are given in the document. So you can draw the DFA by yourself and then compare the answer given in the document. So this is very easy. Don't take load, just practice and you will understand it, and it is easy.